Okay.
Let's make it a prank when we like put like a little turtle shell on them.
Okay, sounds good. All right, let's get started. I have good news. The good news is I think we're going to end early today. Well, you guys are actually a little ahead of the other lecture, and so I kind of want to catch up. I kind of want to balance things, so I'm going to end you guys early and then push them hard to get it balanced. Yeah, this time it's not. Yeah, you're right. Well, it depends on whether I shut my trap or not. That's the big question.
So do you pinky promise we're actually going to go?
No, I don't.
Don't get my hopes up like that.
But I don't think we're going to go late at the very least. This class, yeah, we only have a little bit of enthalpy left to talk about. I don't want to dwell too much on enthalpy because we're going to find out very quickly that it's like really straightforward when we apply it to chemistry. So I got a couple examples today. I'm going to show you some cool online resources that you'll need to use for the homework as well. Just some lookup tables for enthalpies and energies. So actually, this is a very practical kind of lecture because now what we're going to do is we're going to apply enthalpy to chemistry. Applying. Bless you.
Thank you.
All right, we're applying enthalpy to chemistry today. We're doing something actually practical. Okay, everything's been practical. Now it's going to be really practical. The question is let's say we're given a reaction. Let's go back to that reaction that we had before at the end of class last time. So we did a fuel cell reaction. Take 2 moles of H2 gas, a mole of O2 gas, and get 2 moles of H2O liquid, right? If you have a hydrogen fuel cell car, which I'm sure you don't, this is the reaction that causes, this is the reaction that generates the power. And the question is we originally calculated delta H, right? At the end of class, we calculated delta H minus delta U, right? The difference between at constant pressure, the heat released, right? Enthalpy is the heat released or absorbed heat change at constant pressure. And delta U, of course, is the total internal energy of the system. All the energy together, heat and work. Right, we showed that this was largely negative, right, which means that the change in the internal energy outweighs the enthalpy by some amount, 7.5 kilojoules per mole. And we can rationalize that by the fact that there's a phase change going on, right? That there's a significant rearrangement of the system from gas to liquid, right? And so that, in some ways, is work. Right? That's chemical work being done, orderly work converting a gas into a liquid, H2O. And so the total internal energy has a large work component as well, not just heat. So that ends up leading to delta U being greater than minus 7.5. Or delta U greater than delta H. But this is okay, but what about delta H? What is the value for delta H? Right, how much heat is being released or absorbed by this reaction? We don't really have a way to do that yet. So the question is how do we measure that? And the important thing is that we have to remember that enthalpy is a state function. And what that means is that delta H only depends on the starting point and the end point. So let's look at this reaction a little bit. And let's say, for instance, look at delta H for the reaction. So I'm going to write that as delta H Rxn. Well, that's going to be the enthalpy change of the final, which is this liquid H2O, minus the enthalpy of the original state, right? Think of this as the system progressing from one state to another state, right? And the enthalpy change is going to be the difference in the enthalpy of the two states. Right? So delta H of reaction is going to be the delta H of the products minus the delta H of the reactants. Does anyone remember from general chemistry what this law is called? called Hess's law. Hess's law. And we can calculate the enthalpy of a reaction by calculating the enthalpy of the differences. Let's break this down a little more. Well, delta H of the product, well, what is it relative to? This is a change in enthalpy. So what is it relative to? Well, it's the enthalpy of H2O liquid minus question mark. You need to add a factor of 2 for the moles. Right? And the delta H of the reactants is going to be the sum of the enthalpy of each of the reactants. So that's going to be 2 times the enthalpy of H2 minus question mark plus the enthalpy of O2 minus question mark. Now what the heck is a question mark, right? How do we reference enthalpy for an object or a molecule relative to its starting point? What's the starting point for a molecule? Right? Imagine that this process of going differences in enthalpy just carries all the way down. Right? And we have a question is how do we reference the enthalpies of our starting materials or our end material? Right? The question is what do we reference H2 for each species? Because again, we're not measuring energy, we're measuring energy change. Let me explain what I mean by that. Let's imagine that I make an energy scale. So this is energy, increasing energy on the y-axis. And what we measure is, let's call this the initial state and the final state. Initial and final. Right? And the energy difference is just the difference between the two, or difference between the two. This is at energy E initial, and this is at energy E final. But the question is what is energy initial or what is energy final? What is the absolute we of that, right? We can only we measure the difference, but the question is what are we measuring the difference between? Right? Because for instance, I could write this to be 0 and this to be 1, for instance. Let's do a bigger number, 100. Right? And that difference is 100. But I could also write this as minus 999,999 and write this as minus 999,899. Right? And the difference is exactly the same. Right? We would still measure an energy change of 100 joules, or whatever the energy unit is. But the absolute values of these energies can be anything. Right? The energy, in some ways, the energy scale is entirely arbitrary. Right? We can always measure a change in energy by measuring it through, or heat by measuring it with a temperature. Right? We can measure the temperature change. But the thing is what is the absolute scale of everything? Right? What do we set as E equals 0, if you will? So what does H equals 0 define? We have to make a decision about that. In fact, we can set it to whatever we want. And in fact, chemists do determine, they set their, say, their 0 energy scale. They have different definitions of what 0 energy means. Let me see what I mean by that. For instance, let me go ahead and erase this for now. One thing we could do is let's think about the change in enthalpy. Let's define what we call the enthalpy of formation. Which is the enthalpy change of a reaction that forms a molecule, so let's say H2O liquid, from some initial point. All right, what are the products that we're going to measure this change, right? So this is the enthalpy of formation, which we call HF. There are many different ways that we could measure this. One is that we could say, okay, it's the energy change when you take 2 H atoms and 1 O atom to form H2O. But then we ask the question when we calculate this energy change, well, what's the enthalpy of 1H? What's the enthalpy of 1O? Well, that's a problem. Right, so we can't really calculate that difference. Another thing we could do is say, well, we know that H and O don't exist in their atomic forms at room temperature. They exist as diatomics. So we could write H2 plus O2 goes to H2O. And let's balance this equation. We need 2 here and 2 here. And calculate delta HF. Oh, again, we have a problem. Well, what is the enthalpy of H2 and what is the enthalpy of O2? Well, chemists have come up with there's two different formalisms for what we define zero energy, zero enthalpy. And the way that most chemists define zero enthalpy is a species has H equals 0 if it is the naturally occurring form of the species. So therefore, what I mean by naturally occurring is that if we go ask ourselves right now in this kind of what we call a normal environment, Earth environment, how does O usually exist? Well, it exists as O2. It doesn't exist as O. So by definition, we just define it arbitrarily. We can make any point we want, any decision about what sets the energy equals 0 limit. But by definition, we could say, for instance, that the enthalpy of O2 is 0, because that's a naturally occurring form of O2 in gas form. Right? The enthalpy of H2 gas is 0. The enthalpy of carbon as graphite is 0, and so on. So basically the idea is that we want to reference the enthalpy of species where H equals 0 is the most common form of each element. We also have to specify a condition. Are these 0 at 0 Kelvin? Or are they 0 at 298 Kelvin? Typically, we define the condition is STP, which is temperature equals, depends on who you ask, but 298.15 Kelvin. Bless you. Pressure is 1.0 bar. Right? So Earth definition. Right? So we can calculate energy change in a reaction by basically decomposing our reaction all the way down to where we form the original elements in our reactants and our products from the natural elements themselves. So let me explain what I mean by that. Let's go here. So let's calculate delta H for this reaction. And what we're going to do is we're going to calculate the change in enthalpy of formation for each of these. Well, delta H of reaction, by Hess's law, delta H of reaction is going to be the delta H of formation, get rid of that for now, of the products, which is the final state, minus the delta H of formation for the reactants. So let's break that down. Let's look first at the products. How does H2O get formed? Well, we just wrote it down. H2O gets formed, well, it gets formed by this, right? H2, right? The natural form of hydrogen is H2, molecular hydrogen. O2 goes to 2H2O, and let me add a 2 here. Right, so this is the enthalpy of formation for water. And the enthalpy of formation for O2 is 0 by definition, and the enthalpy for H2 is 0 by definition. So when we measure this, measure the heat being released or formed from this reaction, we know what we call the enthalpy of formation for water. Not the most interesting example. But maybe we want to do something with water. For instance, maybe we want to add water and react it with HCl in an aqueous form to form H3O plus Cl minus. How do we calculate the enthalpy of this? How much heat is released from this reaction? Well, we're going to take the enthalpies of the formation of the products and subtract them from here. So the enthalpy of this reaction is the enthalpy of formation of H3O plus the enthalpy of formation for Cl minus the enthalpy of formation of HCl aqueous plus the enthalpy of formation of H2O. Right? And then the question is, well, how do we calculate these? Well, for H3O plus, we would probably want to start with H2 and O2. Let's balance this reaction. 2, 3. Right? This is equal to the enthalpy of formation for H3O plus. Right? And the reason why is because these are 0. HCl will go H2 plus Cl2 gas goes to 2HCl. That's the enthalpy of formation for HCl. And what do we have left? Cl minus. Right, so if we want to measure the enthalpy of reaction for this, we can always calculate it by measuring how much energy is released when we form H3O plus, how much we measure when we form HCl from its elements, and Cl minus from its elements. Right? And then we can just add them all together. Right? So we're bootstrapping our calculation up. Right? We have a complicated equation with a bunch of unknowns. How do we measure each one? Well, then we just break each product or each reactant down into its individual elements and measure those formation energies. Just as a bit of notation, just as a reminder, we call when we write this little dot, this means standard temperature and pressure. A little circle. And then sometimes there's often a subscript here. Now, if you notice, I put the subscript after the H. But in fact, that's not the proper notation anymore. You put the subscript after the delta. This is F is equal to formation. There are many other ones that you'll see. C will be combustion. Sol will be solvation. Right? We can calculate the enthalpy of any sort of chemical reaction. Reaction is just a typical reaction. So you often see these in the book. There's other ones that we'll come across. And typically when you see this right here, the circle, that means that we're at standard, that this is referenced to standard temperature and pressure. That this is the enthalpy of formation or reaction at 298.15 or 1 bar. Of course, we're going to want to, maybe we won't be on Earth, and we want to calculate the enthalpy on Mars. We're not going to want to use the enthalpy of the formation as standard temperature and pressure because on Mars it isn't 300 Kelvin in 1 bar. So anyway, so the idea is that we can bootstrap our enthalpy calculations for any sort of chemical reaction by taking our products and reactants and measuring how much energy is released or absorbed when we form them from the natural elements. Now that's pretty hard to do. Right? If you go in the lab and form H2 plus Cl2 gas to form HCl liquid, you're going to have a bad time. It's a pretty tough reaction to do. This is also a really hard reaction to do as well. But you can imagine there might be a cleverer way you can take this reaction and break it down into 2 sub-reactions that you can then add together that will sum to this one. And that's often a clever way to do it. But what I want to emphasize, though, is this idea that we can calculate how much heat is being released or absorbed by a reaction just by referencing how much heat is being released or absorbed by the formation of each component of our reaction and calculating the difference between the products and the reactants. So just as a reminder, Hess's law says for a reaction where you have reactant 1 plus reactant 2 all the way to reactant N goes to product 1 plus product 2 all the way to product N, that the enthalpy of the reaction is the sum from I equals 1 to N of the enthalpies formation of the ith product. I'll write it like this instead. P sub I, the products, minus the sum of I equals 1 to N, the enthalpies of formation of the reactants. Bless you. Oh, times the there's also stoichiometric coefficients as well. So I'll write that N1, N2, right? They might have multiple stoichiometric coefficients, M1, M2, Mn. This is Mn, Rn, sorry. N sub n. So this would be times N sub I minus times M sub I. All right, we have to multiply them by the stoichiometric coefficients. All right. So now the question is where the hell do we find enthalpies of formation? All right, maybe you're given a reaction in lab and you need to calculate whether it's going to be. Maybe it's a good time to mention these terms. I'm sure you've used these before. All right, if enthalpy is greater than 0, we call this endothermic. This is a reminder. And if they're minus H is less than 0, they're exothermic. Right, so maybe you're given a reaction that you are in lab and you're curious if it's endothermic or exothermic. Well, you can predict that very easily by looking up the enthalpies of formation. Right? There must be some crazy chemist out there who measures all of these. And in fact, there is. Right, so given any reaction, you can always figure out how much energy it's going to change by measuring the enthalpies of formation of each of the products or reactants. And I want to show you a couple resources for that. Of course, one place you can find them is in the back of your textbook or any general chemistry book. There's always a number, but that's a pretty small resource, and it's mostly just kind of common chemicals. But there are a number of lovely resources online for calculating these things. The first one that I'll show you, and maybe you guys have been to this before, is the NIST web book. Anyone ever been on this web book before? Okay, so does anyone know what NIST is? Does anyone know the term NIST?
National Institute of Science and Technology.
Standards and Technology. So NIST is a Department of Commerce division. It's a division of the Department of Commerce. They're the ones, they're the official timekeepers and standards calibration keepers of the world. They come up with, they're ones that maintain, for instance, the U.S. clock. The Naval Observatory also does in conjunction with NIST. They're also the maintainer of most standard reference information for physics and all science, especially physics and chemistry. They also do a million other things as well. Any sort of, if you ever encrypt data, the people who validate encryption and certify encryption routines is NIST, or the ones that also do that in conjunction with the the NSA. But NIST has this thing called the Chemistry Web Book, and it's just a giant database of chemistry information. And it has all sorts of really cool stuff. You can get enthalpies, heat capacities, entropies, vapor pressures, IR spectra, mass spectra, UV vis spectra, gas chromatography, you name it, for any data, for any molecule you want. So for instance, let's just type one in. Let's look at H2O, water. And so there's all sorts of information about water. But notice there's two particular interesting things for us, gas phase and condensed phase thermochemistry data. So let's, for instance, go to gas phase. And here it'll tell you exactly what the enthalpy of formation for gaseous water is, right? So this is the reaction, I don't really have room for this, of H2 gas plus O2 gas goes to water liquid. Right? And you can look up the exact value for it at, again, standard temperature and pressure, which is that little circle right there. Right? So you ever see that circle, that means 1 bar and 298.15 Kelvin. All right, so you can always find enthalpies on here, amongst other data that's useful. Once we get to entropy, we'll talk about that as well. You can find heat capacities on here. We'll talk a little bit more about that in just a second. So this is a really nice resource for this kind of stuff, because we're going to be, in the homework, there's a number of different enthalpy, reaction enthalpy questions, and you're going to have to look up the enthalpies of formation for different things. So this is a really good resource for that. Another really good resource, yeah, question?
For the enthalpy formation, is that something we'll ever have to calculate, or will it all be?
No. Enthalpies of formation, you can just pull off of here. Yeah. There might be a situation. Yeah, so for instance, last year I gave an exam, and one of the questions was about how to determine enthalpies of formation. And because some enthalpies of formation are really, really hard to measure directly. And so what sometimes scientists will do to be clever is to basically take two reactions that when you add them together, the net reaction ends up being the enthalpy, the formation reaction. So you have like an intermediate step. And you add two reactions, and then the net reaction is the formation step, the formation reaction. And those two sub-reactions that we measure, that we add together to get the net reaction, those tend to be, they might be easier to measure experimentally. And so you can calculate enthalpies of formation by summing together two enthalpies of reactions. So I can see a question like that, but to calculate enthalpies of formation straight up, we'll never do that. These are experimentally known numbers. Now, what I haven't described is there's a way to technically calculate these numbers without, you can predict a value for this number using computers, but we won't do that. And I'll talk about that very briefly, about how we can determine these theoretically. But typically, this is an experimental number, and these are typically measured experimentally. But you can predict them using computers, and I'll talk about how they do that briefly in a minute. Another place to find it is this website, atct.anl.gov. Active thermochemical tables. I learned about this. This is a project out of the Argonne National Laboratory in Chicago, which is a Department of Energy lab. It's actually the place where civil nuclear power was first invented and developed in the 1940s, early 1940s, or late 1930s, early 1940s. Enrico Fermi and his associates built the first nuclear critical mass, nuclear reactor, if you will. And they did it under the steps of the badminton gymnasium at the University of Chicago, right? So they had this big masonry, basically a giant, like a igloo of brick. And inside of it, they stuck a bunch of uranium. In order for uranium to reach critical, to become critical, you have to have a certain amount of certain density and a certain mass of reactive uranium. And so they put it there and measured the heat being released by this once it reaches criticality. And they did this in the gymnasium. And then they immediately realized that maybe it wasn't the best idea to create a nuclear reactor in a gym. So the government built a secret facility in the forest outside of Chicago where they built the second nuclear reactor, Fermi and a number of other people. They call it the Chicago Pile No. 2. And they built it out in the middle of a forest, and they put huge fences around it. And they created the second nuclear reactor on this facility in what's called the Argonne Forest outside of Chicago. And then when it was done, they buried it. In fact, you can go to the forest, and there's a little sign there that says, "Here lies the second nuclear reactor ever built." They buried it deep in the ground. And since it was so successful, the government said, okay, well, we're going to build Los Alamos to build the bomb, but we can also generate power with this technology. So they created Argonne National Laboratory outside of Chicago to develop civil nuclear reactors. And Argonne's the site of the first functioning civil nuclear reactor. The first civil nuclear reactor was barely powerful enough to power a light bulb, which is crazy. Of course, now nuclear reactors can generate millions and even billions of watts of power over the course of a year. But the first nuclear reactor could barely manage 20 watts, I think, or something like that. It's a very small amount. So anyway, so now they do energy research, batteries. There's a lot of battery research at Argonne. But there's this old Croatian guy who was actually my office neighbor when I was there. And his entire job, his entire career, is tabulating thermochemistry data. All right, he spent his entire career trying to accurately calculate enthalpies of formation for chemicals. That's his specialty. And this is his website. And he updates it constantly. He still works. He's in his 70s, but he still works. This website has thermochemical data for more molecules than you can count. And I'll just show you. There's different versions, but I'll pick the most recent version. And here, all you have to do is just type in a species. You can give it a chemical formula, or you can just click one from this list. And so, for instance, dihydrogen, here's the first result, H2. And he gives you the enthalpy of formation at 0 Kelvin and also at 298.15 Kelvin. Right? Sometimes the 0 Kelvin number is useful for certain types of reactions. But he also gives it to you in 298.15. And these are in fact, and he also gives you the uncertainty, which is the amazing thing, is that this is in some ways the most precise and the most well-tabulated list of thermochemistry data in the world. Very, very accurate. And he has a really long, complicated way that he calculates these things in a very unique way that other chemists don't use to get really, really good uncertainties on his values. So if we go down this list, you can see almost everything on this list is 0 because these are the natural occurring states of each of these atoms, right? H2, single helium, graphite carbon, nitrogen gas, O2 gas, fluorine gas, neon, and so on and so forth, right? So when you see 0, this is what we define as 0 energy for chemistry, right? This is how we reference energies for everything. Are these simple elements? And so let's take something a little more interesting. So for instance, let's look at methanol. For instance, right here's methanol. Methanol has a negative enthalpy of 190 kilojoules per mole of formation. plus or minus 0.15, or 200 at, the interesting thing, and we'll talk about this in just a minute, notice that the energies, the enthalpy is different at a different temperature. Right? So when we go from 0 Kelvin to 298 Kelvin, forming methanol from its original elements, which would be H2, carbon, and O2, it actually releases more heat at 300 Kelvin than it does at 0 Kelvin. Enthalpy is not constant with respect to temperature, so that's interesting. And we'll come back to that in just a minute. All right, so you can look up any molecule you want. They're all on here, even molecules that are really obscure. Right, things like the methyl radical, right, CH3 radical, for instance, which has a positive enthalpy because this is high energy. Right, if you think about this as being CH4 going, if the formation of this is taking methane and plucking hydrogen off, you have to break that bond, so this is going to be positive, right, and so on and so forth. But the cool thing about this paper, or about this website, is the information that it gives you. This is kind of not super it's kind of nerdy, it's not super practical, but it's really interesting. But if I take methanol, for instance, and I click it, it opens up, again, a picture of the molecule, the results. But the cool thing is that the way that he determines this is by taking, in the literature, thermochemical data of various reactions containing methanol. Right? So every single one of these reactions has a contribution to its overall enthalpy from the formation of methanol in the gas phase. Right? And so he's got here, the reference for each measurement. Here's the different enthalpies for each of these reactions. And he sets these up in a big network. And then basically uses this data to back calculate the enthalpy of formation for methanol. And he does it from multiple sources. Right? And the cool thing is he weights the contribution. He says if a reaction's really well known, right? This one's really well known. It has very low uncertainty compared to some of these other ones, right? This one's 0.05 kcals per mole on the uncertainty, but this one's 0.39. Right? They're about an order of magnitude higher. He weighs that higher because he knows that's a more precise measurement. And so he takes all of this data, all these reactions that chemists measure, and then basically does Hess's law, just does the algebra, and then takes all these reactions and sums over them to solve for the methanol enthalpy of formation. And he propagates the uncertainties, weighs them depending on their contribution, and gets an average result, which is this number right here. Right. So in some ways, if we look back at NIST for methanol, the enthalpy of formation for NIST comes from one source, right? There's some agreed upon paper that the enthalpy of formation comes from, all right? And so it's just the value is sourced from a single piece of data that they think is the good reference data. But the really powerful thing about this technique that Branco does is that he says, well, all measurements are good, but some are better than others, but we should include all of them together and then average over them, because sometimes the less known things will help us adjust the values a little bit, as well as the things that are well known. And so he statistically weighs all of these together to give you the most accurate and precise value for the enthalpy of formation. Not only does he do that, but you can also see the things that are correlated as well. The other species that are correlated with the formation of methanol, things that often appear in reactions that form methanol, right? So, for instance, methanol is associated with itself quite a bit. Things like protonated methanol, right? It's H2C plus, right? You lose an H minus. Methanol cation, right? This is pluck an electron from methanol. Methoxy, right? We remove the H from O. Methoxide, where we pluck the hydrogen off and leave the electron. This radical, CH2OH, right? You pluck a hydrogen off that. Right, so these are the molecules that help contribute to our understanding of what the enthalpy of formation of methanol is, right? And this system is networked, right? So it's always everything's interconnected, right? So if we go to one of these, for instance, methoxy, right? We can see everything, and then you can see the things that methoxy is related to in terms of its enthalpy understanding, right? Maybe people often learn about methoxy by doing these deprotonation reactions with toluene. Or here's methanol again, right? So everything's interconnected in this network. It's a big network of molecules, and we have many, many different reactions and studies, and they're all combined together and statistically weighted so that we get a very, very precise result for everything. Okay, so this is the cutting edge of thermochemistry. Now that seems kind of like a trivial thing, but this is a lot of work, and it's a very, very, this is what's typically cited when we do thermochemistry at the research level. We usually cite ATCT for these things. So there's a couple problems on the homework where you have to calculate some reaction enthalpies from formation enthalpies. You can just look them up on ATCT at the temperature, at one of the temperatures, depending on which temperature it is, and just plug them in. Okay. Any questions about that? Yeah?
Are these like linked on Canvas, or can they be?
I will be. I'll put them on Canvas for you. Yeah, that's a great idea. Yeah, let me make a note of that real quick. Yeah, I'll post links after class. ATCT and NIST webbook links. Okay, I just want to talk about one more thing, and then we'll be done for the day. So the thing I want to point out is that the enthalpy for all of these, right, you can just go down a list and you can see that the enthalpy of formation for a product is different at different temperatures. Right? So at 0 Kelvin, we have 230, but here it's at 211. Right? So something's changing. Enthalpy is a temperature-dependent quantity. And I want to talk a little bit about where that temperature dependence comes from. Because again, that's an important thing to know, because if we want to calculate a reaction on Mars versus the Earth, and we know that the enthalpy changes as a function of temperature or pressure, we need to account for that. Or if we're doing something at high temperature and not room temperature, like you're maybe synthesizing ammonia from N2 and H2, you're going to do that at high temperature and high pressure. You're going to have to, if you want to know how much energy that reaction releases, you're going to want to be able to calculate the enthalpy at a particular temperature. So I'm going to introduce a very simple law. It's called Kirchhoff's law, which gives us a relationship between the enthalpy at standard state and the enthalpy at any temperature. So let's say at T equals 298.15 Kelvin, P equals 1 bar, the enthalpy of the reaction is this. All right, and then we want to ask the question, what is the enthalpy at some new temperature, T new? Kirchhoff's law gives us a nice response. Kirchhoff's law says that the enthalpy of reaction at our new temperature is the reaction enthalpy, say at standard state. Of course, it could be at any state. You could do it at 0 Kelvin if you wanted. It doesn't matter. So we'll say 298.15 in this case. And then there's a correction factor. And the correction factor is integrating from 298 to T new of the heat capacity at constant pressure times dT. Right? And a way to think about this is that the heat capacity is the change in enthalpy over the change in temperature at constant pressure. And I'm going to do kind of some really wonky math here. If we multiply both sides by dt, then we have that the change in enthalpy is equal to the heat capacity times the change in temperature. Integrate both sides from T1 to T2. This is just the enthalpy at T2 minus the enthalpy of T1 equals this integral. Right? And that's the exact same thing we have here, right? We have the T2 minus h of T1 equals the integral of the heat capacity with respect to temperature. All right, so it's a pretty straightforward idea. So if we can measure the heat capacity of a substance, we can now take the enthalpy of anything and convert it to a different temperature. So let's try that real quick. So let me give you an example. So let's take the reaction, the formation reaction of benzene, which is where you take six carbons, 6 graphite atoms, and add 3 equivalents of H2 gas to get benzene. Okay, so that's the enthalpy of formation. The enthalpy of formation for this reaction at 0 Kelvin is 100.61 kilojoules per mole. Now, the reason why we reference things to 0 Kelvin is very interesting. Why is this number? Of course, as you will find out, getting to 0 Kelvin is impossible experimentally. We'll find that out in the third law. So why do we even think about the enthalpy of reaction at 0 Kelvin? Well, the reason why we do this is because it's really easy to calculate the enthalpy of formation of the molecule on a computer at 0 Kelvin. The way that computational chemists do this what they do is they take 6 carbon atoms, and 6 hydrogens, all separated at infinity. All the atoms are gone together, right? So they measure 6 times the energy of a hydrogen atom and add it to 6 times the energy of a carbon atom. These two are easy to compute with a computer. So let's say the enthalpy of hydrogen, rather. The single atoms, and they bring everything together to form benzene. So a computational chemist doesn't use H2 and C2. They just blow everything up into their atomic components and separate everything out to infinity so no atom is touching each other or interacting. And then they bring them together and then also calculate the enthalpy of benzene for a single molecule. All right, a single molecule can't have a temperature. So it's at 0 Kelvin by definition. And they calculate the energy difference. They calculate the energy of benzene by using quantum mechanics. They calculate the energy of a carbon atom by quantum mechanics at 0 Kelvin, and the energy of a hydrogen atom at 0 Kelvin, and then calculate the difference. Right? So the enthalpy of formation for a computer is the energy released or absorbed upon forming one molecule from its atoms. All right, so they don't use this standard state of hydrogens, H2 and graphite atoms and O2. Right? They just blow everything up to their atomic counterparts and then put it all together and calculate the energy difference. It's not hard to it's not hard to calculate what we call the energy of this system relative to the energy of the atoms. Right? A computer can do that using quantum mechanics. That's the whole point of quantum mechanics. One of the reasons. There's many reasons we use quantum mechanics, but one of the powers of quantum mechanics is that you can calculate the energy of any molecule. Right? And so the energy of formation is just the energy difference between the atoms and this at 0 Kelvin. So it's a useful number because we can calculate it. We can predict it using computers. All right, so back to the problem so what is enthalpy of, what is delta HF of benzene, right, at 298? Okay. So we can use Kirchhoff's law for this. And Kirchhoff's law says Kirchhoff's law says that the enthalpy of formation at 298 is equal to the enthalpy of formation at 0 Kelvin plus the integral from 0 to 298 of the heat capacity of benzene times dt. Well, in order to calculate this, we need to know the heat capacity. Well, we could just look that up. The heat capacity of benzene at 298 Kelvin is equal to 135.7 joules per mole per Kelvin. It's just a number. So if we assume Cp is independent of temperature, the enthalpy of formation at 298 is the enthalpy at 0 Kelvin plus Cp 0 to 298 delta T, which is the enthalpy of formation at 0 Kelvin plus Cp times the change in temperature. So that's 100.61 kilojoules per mole. And then we need to convert this to kilojoules. Cp is 0.1357 kilojoules per mole per Kelvin. And our temperature difference is 298 Kelvin. Right, go from 0 to 298. Right, and this is that the enthalpy of formation of benzene at 298 Kelvin is 141.06 kilojoules per mole. Sorry, that's not enough. All right, cool. So we've got a nice, we can predict this number. All right, so let's go look it up. Let's see if we're right. So what we predict is that that this reaction is more endothermic as temperature increases. Right? We went from, as a reminder, from 100 to 141. So let's go look in ATCT real quick. I'll move the screen up a little bit while this turns on, sorry. So you can write that down. And let's go look up the benzene formation at 298. So chemistry data, and type in C6H6. Find. Oh, they're case sensitive. My apologies. .23. It's the opposite direction. We did something wrong here. All right, what this says is that the system becomes a more exothermic reaction or less endothermic reaction as the temperature increases. But we predicted the opposite direction. What do we think we're doing wrong here? Any questions? Any ideas?
Maybe should it be going from 298 to 0? Like, get a little bit backwards.
Well, let's do that. So what is that? Does someone want to calculate that real quick for me? I'm going to spoil it. This might coincidentally turn out pretty close, but that's not the correct answer. This is the correct answer, but that's an interesting point. I think coincidentally it comes out right. Yeah, what is it if you subtract this?
About 60.
60, so it's too low. It's too low now. All right, everything we've done here is general. There shouldn't be any reason this doesn't work. But there's a particular approximation that I just made that I haven't really pointed out, and it's that we've assumed that the heat capacity is independent of temperature. And in fact, what the idea of a heat capacity is, there are many different. The idea is how much energy does the system store before it releases enough heat to raise the temperature by 1 degree. Right? So the more ability a molecule has to store energy, the higher its heat capacity is. And the fact of the matter is that as you raise the temperature of a material, more arrangements of that system become available, right? It's got more energy to use at higher temperature, and it can access more storage modes of energy internally. So in fact, the heat capacity is going to change as a function of temperature. And let me show you what I mean by that. So if I go back to NIST, and type in benzene, gas phase thermochemistry data. Notice here on the, let me put the screen down real quick so it's easier to see. Notice here that as temperature increases from 50 to 3000 Kelvin, the heat capacity of benzene increases from 33 joules per mole per Kelvin. It's almost 10 times that order, the magnitude. 270. And so the heat capacity is increasing because as benzene gets hotter, there are more arrangements for a gas of benzene to access and more ways for it to store energy through vibrations or rotations or any sort of motion. And that increases the heat capacity of the gas. So in general, heat capacity increases with temperature for most species. Oh, these are constant pressure heat capacity of gas, yeah. So let me see where that is. Right, so we have to be more careful. We can't assume that the heat capacity is constant. Let me see if I have this somewhere here. Just a sec. I'm looking for the heat capacity table here. I can't find it. That's okay. So in fact, what happens is, just briefly, every species of molecule, or every atom has some sort of temperature dependence to its heat capacity. So let me go ahead and erase this. And so the thing is that, let me just write Kirchhoff's law one more time. Is that heat capacity is a function of temperature, so we need to integrate over that function of temperature. For instance, for benzene, typical, you can measure the heat capacity as a polynomial in T. For instance, this is the experimentally determined heat capacity function for benzene. Notice that notice it's just a polynomial. It's just an approximation, approximate function. And notice that the contribution gets smaller as the power of t gets larger, right? So there's a large linear term, large constant term. Right, if t is 0, this is the heat capacity of benzene at 0 Kelvin. We can add a little bit of temp. We can add t here. The t term is a little bit smaller, but it's still fairly large. And then it gets smaller and smaller as we go up. Right? So at high temperature, this starts to become more important, but at low temperature, the t cube term doesn't change that much. Right, so in order to calculate the enthalpy of formation for benzene, we have to instead integrate this function with respect to t from 0 to 298. But unfortunately, it gets even more complicated because, well, let's do it. Let's try that. All right, so let's do that real quick. So delta HF. So HF0 is 100.61. Plus the integral of this thing right here. I'm just going to put it right here. dt, integrate from 0 to 298 Kelvin. And then when we integrate this out, I won't do it out because again, we can plug this into Wolfram alpha and have it evaluated for us. Or I can just write it. When you do this integral, you get 81.865 kilojoules per mole. Now, the experimental value from ATCT that I just showed you was 83.10 kilojoules per mole. Right, so we're very, very close. And so the important point, take-home point, is that enthalpy is temperature dependent. And heat capacity is temperature dependent. Okay, so in order to calculate and extrapolate properly and to calculate an enthalpy, say, of 1,000 Kelvin, we need to account for the fact that the heat capacity is going to change significantly from 298 to 1,000 Kelvin. Notice that this is, even though this seems complicated, it could be a lot worse. Because the advantage is that the enthalpy of formation at 298 Kelvin for our starting products, carbon and hydrogen, is 0, and it's also 0 at 298 by definition, right? It doesn't change. So we only have to calculate the change in C6H6. But imagine that this reaction had multiple molecules where the enthalpy of formation was not 0. Then you would have to calculate how the enthalpies of formation change for each species as a function of temperature. Integrate each one separately. Right? We would take this one, let's say this is at 0 Kelvin. We would boost this one to 298 Kelvin. By using Kirchhoff's law, we would boost this one to 298 Kelvin. Boost this one to 298 Kelvin. We would have new values at 298 Kelvin, and we could calculate the difference there. All right, so that's the nice thing about this being a state function, enthalpy being a state function, is that if we want to take a system at some state and we want to convert it to some other state, all we have to do is just use a little bit of arithmetic and boost all the numbers independently for each species, and then use Hess's law to calculate the enthalpy. I'll draw that in a figure real quick for you. All right, so let's say we have a reaction A plus B goes to C, and we have an enthalpy of reaction at 0 Kelvin, and we want to calculate the enthalpy of reaction, let me correct this reaction, at 300 Kelvin. How do we do that? Let me just write A plus B goes to C here. Well, what we do is we take the enthalpy of formation and apply Kirchhoff's law to take it from 0 to 298 Kelvin, or 300 Kelvin, for the products. And we do the same thing for the reactants. Right? So we use the integral of Cp dt from 300 to 0 for each species. Right? And then we get new enthalpies of formation at 300 Kelvin. And then the enthalpy of reaction for this reaction at 300 Kelvin is just the enthalpies of formation of the products minus the reactants. Right? So that's the advantage of doing a state function, is that we can decompose changes in state in a very simple way. Right? If we can take each component of our system or our reaction, boost them individually, and then calculate the difference or the change in the energy at the new state. Right? So in order to, if A and B had non-zero enthalpies of formation, we could calculate the new enthalpy of reaction by calculating 3 integrals, one for each of the enthalpy of formation and heat capacities for each of the species in the reaction. Get us new enthalpies of formation up here at 300 Kelvin, and then just calculate the difference of the products minus the reactants at 300 Kelvin. Right? And that's thanks to state functions. Okay, so we are going to finish early, about 5 minutes, so that doesn't really count, I don't think. That's all I have to say about enthalpy today. So there's some simple enthalpy problems on the homework. On Tuesday, we'll start entropy. All right, and then once we have a little understand entropy, we're going to dig into some real practical thermodynamic problems and thermodynamic processes. Have a lovely week.